All right, the lesson today we're talking about is the second half of 8.6, and we are still working on radical expressions and rational exponents. And today we're going to focus more on rational exponents, or fractional exponents was our focus today. So a rational exponent is an exponent that can be expressed as m over n. So we're looking at fractions. M and n are going to be integers, meaning positive or negative whole numbers, and n, the denominator, cannot be 0. A radical expression can be written by using rational exponents. So this is something that we have talked about, but we are officially doing this now. So if I have a to the 1 over n, so here it is, I have my base of a, and I have a rational exponent of 1 over n. Remember, rational numbers can be written as repeating or terminating decimals, or written as a fraction. Any fraction would make a repeating or terminating decimal. So that is why they're rational exponents. If I have a to the 1 over n, that is equivalent to the root form, the nth root of a to the first. All right? The denominator is our root. The power comes from the numerator. So the nth root of a, n is the index. Here is our radical symbol. A is the radicand. All right, so let's show an example. If I give you 16 to the 1/4, that is the same as, keep the 16 under here with the power of 1, and the denominator was 4, so my root is 4. So that's if I have 1 over something. If I have it more general as a to the m over n, whether m is 1 or 2 or 4, does not matter, but the idea is the root comes from the denominator, and the base is now your radicand with the power attached. So I want to remind you in the order of operations that roots fall right in with powers. They're inverses, just like multiplication, division are inverses, roots and exponents are inverses. So they are hand in hand. So when I look at something like 8 to the power of 2/3, all right, I can type that in my calculator if I could find it. Okay, so I have my calculator. I can type in, and I have to be careful how I do this, I can type in 8 to the power of, and I can type it in as 2 fraction 3, as long as I use my fraction key, and I get 4. But if I type it in, and let's say I'm using a graphing calculator, I try to type in 2 divided by 3, I use my division symbol as a fraction, it's going to take 8 to the power of 2, 8 to the power of 2, because order of operations, it's going to get that answer and divide by 3. I get a very different answer. So I think do 8 to your power, and I say just to be careful whether I'm using the fraction key or I'm using division key, go ahead and put anything in your power in parentheses so it knows you're taking the whole thing. Again, if I do that with the division sign, now it knows it's 8 to this. Take 2 divided by 3, use that as my power, and I get 4. All right, now we need to be able to do these without using a calculator, so let's talk about that. In my head, I don't know what 8 to the 2/3 is. Mentally, I'm just not grasping it. So I think best to change it to a root. Okay, so I'm going to take my fractional exponent and change it into root form. So that would be the cube root of 8 squared. Now there's 2 ways I can attack this. One way is to look at this and say, okay, this is the cube root of 64, right? Because 8 squared is 64. And then if I'm not sure what the cube root of 64 is, I would type it in my calculator. Many of you probably know it because it's used often. So how do I type it in? Type in my 3 and then define it as the x root. So that is the 3rd root of 64, and we get out 4. Perfect. So I get an answer of 4, just like the calculator had said. Now, the other way I can look at this is it's equivalent to saying it's the cube root of 8 all to the power of 2. So it does not matter whether your power is on the number or it's outside of the root. Now, again, it would be proper to put this in parentheses, especially if I have a negative sign there. All right, so be careful with that. Because the whole thing had the power to it. But if the negative sign was on the outside, it would stay on the outside. So be careful with that. But the idea is I could, instead of taking 8 squared first, I could take the cube root of 8, which is 2. Again, you put that in the calculator. And then take that and square it, which also gives me 4. So if it's a problem where I can take the cube root of the number, I'm probably going to take the cube root first, get a small number, and then do the power. Sometimes we have a big number here, and then taking it to power, it makes it a huge number to then break down. And remember, we want exact answers, so there are times that you have to break it down. These rules are really important, and it's important that you have a note card and you keep your power properties on it, and these go hand in hand with those properties. All right, so it looks like we're jumping ahead. Remember, this is a continuation of 8-6, so we're starting with example 3. We completed examples 1 and 2, working with roots and variables in the last lesson. And remember, we did that. We broke them down for exact form as well as rationalized denominators. Okay, so write the expression -1/25 to the 2/3 in radical form and then simplify it. So it's a two-part problem. The first thing I'm going to do two methods, just like I showed you up above. First thing I'm going to do is I'm going to write it as a radical. So notice this is in parentheses. So the power of 2/3 is on the negative sign and the 125. That's a big deal. So when I go to write this, I'm going to put that -125 in parentheses. Now, it's to the power of 2/3, so the root is 3 and the power is 2. Now, in this problem, the way I would like to do it is I'm going to evaluate the root first. So I'm going to leave my power out there. The cube root of -125 is -5. And again, you might want to double check that on the calculator, but I still have a power of 2. And notice my parentheses are here because -5 squared is going to give me a positive 25. I think this was the best way to do this problem because I could take the cube root of -125. I'm dealing with something smaller. Now, the other way to evaluate, especially if this wasn't a cubic number, the other way, we would still change the form, still use the parentheses, but instead of taking the cube root first, I'm going to square this. Now, I don't know what -125 squared is. So notice I'm using parentheses because when I square it, the negative sign is going to cancel out. And I end up with the cube root, notice I keep bringing my index down, of 15,625. All right, well, I know what the answer is going to be, but if I didn't know the answer, the first thing I would do is I would take and define my cube root of my number. Maybe I would just hit second answer, but I'll type it in here. And I'm going to try it. And I lucked out that this is a cubic number, and my final answer is 25. However, if this wasn't a cubic number, then I would be taking the time to break it down. Okay? So I think I would always try to break it down first and then work from there. But if this did not have a cube root, maybe I would square it and then I'd be able to break it down. All right, this is a great place to pause and try these 3 check it out problems. All right, so first we're going to put it in radical form and then we're going to simplify. So there's 2 parts to the answer. So the first thing I see is 64 to the 1/3. In radical form, that would be the cube root of 64 to the 1st. I don't have to show that power of 1, but I want to make sure you remember that it's there. What is the cube root of 64? Well, it's 4. That's it. I'm done. Nothing extra. This would be the square root of 4 to the power of 5. Now, notice I don't have to put the 2 there. The square root is your common root. It's understood. But you could put the 2 there to show it. You could take 4 to the 5th. I am choosing to take the square root of 4, which is 2, and then go to the 5th. And you want to double check yourself. Remember, you're not multiplying. It's 2 times 2 times 2, 5 times, and we get out 32. Now, the other way you could have done it is you could have taken 4 to the 5th, which is 1024. So then we would have had the square root of 1024, and then we would take the square root of 1024, and we would end up with that same outcome of 32. But I could do this a little bit easier. All right, next one I have the 4th root of 625, all to the power of 3. Now, none of these had parentheses, so I didn't put parentheses around them. I could, if there was a negative sign outside of the parentheses, then that should not be in parentheses. Okay, if there was a negative sign here, I couldn't do this problem because I cannot take a 4th root of a negative. I can take a cube root or a 5th root, but I cannot take an even root of a negative. All right, I have no interest in taking 625 to the 3rd. That's a big number. So I'm going to see if there is a fourth root of 625. So again, type in your 4 to find your root, and there is. So we have the fourth root of 625 is 5, but I still need to take it to the power of 3. Again, double check yourself. I get 125. Okay, so very important to be able to change it from exponential form, so rational exponent, to root form, or from root form to rational exponent form. All right, well, that's what we're doing next. So each problem I'm going to write as a rational exponent. And then we are going to go ahead, if we can simplify it, we will, but these don't simplify very nicely. So looking at this, here's my rule. If I have the nth root of a to the m, it's the same as a to the m over n, or I can reverse it. If I have a to the m over n, it becomes a root, the nth root of a to the m. All right, so looking at my first problem, my base is 7. My power stays as 3 with the denominator of 4. And that's all I can do there. Again, it's actually easier to evaluate them in root form. There is no fourth root of 7. All right. If I would have taken 7 to the third, whoops, I get 343. There is no fourth root in 343. So we're not being asked to simplify this. Again, we're just changing the form here. All right. The other thing I want to let you know, it's not proper. Like, this would not be your answer. So answer, if you had this, you would take it back to root form, but you would never leave a power here. You would always, expand it and put the power, multiply it out. Okay, looking at this, there's no cube root of 11. 11 to the 6 is a big number. We're not going to be able to break that down right now, but I want to show you, if I was writing this, this would be 11 to the 6/3. Just as always, you're going to reduce that fraction. So this would really be 11 squared, which this one we can simplify. It ends up being 121. So it was much easier to take this root, change it to exponential form, and then reduce it, and it's 121. I never had to take the cube root of anything. All right, so always simplify your answers. So here's one that was all we could do. Here's one we could simplify it down. All right, so again, here's some check it outs. All we're doing is changing form, and if you can simplify it, we can. The first two simplify, the third one does not. All right, so looking at this, this would be 81 to the 3/4. Now, 81 to the 3/4 is not how I'm processing it. I would actually process this. And so if I come back to this, there is a fourth root of 81. It's 3, and then I take that to the power of 3, and I end up with 27. So this is my rational exponent, and this is what it simplifies to. But again, I like to work in the roots. I don't want to take 81 to the third. I want to take the fourth root of 81, break that down if possible, and then take that to the power of 3. All right, looking at this one, it'd be 10 to the 9/3. Okay, you're not going to leave me that answer. You're going to tell me it's 10 to the third. So that is how it is written as a rational exponent and simplified. And I get out a total of 1,000. We can simplify that. All right, looking at this next one, there is no fourth root of 5. I could take 5 squared and then try. But the idea is, as a rational exponent, it's 5 to the 2/4. Now hold on, we don't leave that. That would be 5 to the 1/2. And then this is not going to give us a nice rational answer, because 5 to the 1/2 is the same as the square root of 5, right? 5 to the 1/2, square root of 5 to the first. So we would just leave that answer there. Okay, now we're going to go back. I'm going to try to get through this quickly. All these power properties came from a previous lesson in chapter 1, and it's something that we have talked about throughout the year. So these really need to be well known, and they're going to be used for every other math class you take. And so you want to make sure you know these. Again, keep referencing a note card, make sure you have them. So algebraically, and we went over these in the last lesson, if I have a to the m times a to the n, if I'm multiplying bases, I keep the base and I add the powers. Now, if we're dealing with numbers, and I have 12 to the 1/2 times 12 to the 3/2, that's why we were reintroducing it. I'm not dealing with integer exponents. I'm dealing with rational exponents. I still follow the rules. I keep the base of 12 and I add the 1/2 and the 3/2. So when I go to do that, I need to be good with my fraction rules. That's why we spent some time going over those. And 1/2 plus 3/2, that really gives me 12 to the 4/2, which cleans up to 12 squared, and we know that is 144. So again, when I multiply bases, I add the powers. All right, quotient. When I'm dividing, I subtract. So I keep the base and I take m minus n. All right, so looking at some numbers, I have 125 to the 2/3 over 125 to the 1/3. Now remember, the bases have to be the same. And we were doing these with integer exponents, and when we had it to a whole number, we would just sort of cancel them. Well, we're going to keep that base and actually show the subtraction of, it's going to be 2/3 minus 1/3, which gives me 125 to the 1/3. Well, we know 125 to the 1/3 is the same as the cube root of 125, which gives us 5. Same rules. All right, power to a power. This rule has always been that you multiply. So you keep the base, power to power you multiply. Don't get that confused with when you're multiplying you add bases. So how does this one look? Let's take 16 times 25 to the power of 1/2. So the idea here is that I don't want to take 16 times 25. That's a really big number. But if I can break this down and look at it as 16 to the 1/2 times 25 to the 1/2, and I recall that a power of 1/2 is the same as a square root, I can do it pretty simply. So let me show you that again. This is the square root of 4 times the square root, it's a square root of 16, which is 4. Square root of 16 times square root of 25, and that would be 4 times 5, and we get a simple answer of 20. Could I put 16 times 25 together? Absolutely. Could I type this whole thing in the calculator? Absolutely. But we're going to be dealing with variables, so we want to make sure we can use our rules properly. All right, power of a product. We can distribute powers over multiplication and division. So here's distributing over multiplication, not addition or subtraction, multiplication and division. So if I have an error here, I apologize. I am not going to re-record this, but I actually flipped my rules here. When I did this rule, this should be down here. So I'm going to fix that, and I apologize. So this would be 16 to the 1/2, and we did everything right. Mathematically, you distribute the power. I had just jumped rules there in examples. So that would be the square root of 16 times square root of 25, and we have 4 times 5, and that gives me 20. This rule was down here. We were distributing a power. I did not do the power to the power. So I'm going to block all this out. So mathematically we're right. We were just under the wrong rule. Okay. All right. Sorry about that. Thank you. So I'm going to show you an example of a power to a power, which is 8 to the 2/3 to the power of 3. And that is going to equal, okay, so when I have a power to power, I multiply. And so that would be 8 to the 2/3 times 3. Okay, well, if I take 2/3 times 3, the 3's cancel out. I get 6 over 3. Any way I cut it, I get 8 to the power of 2, which is 64. Okay, so thanks for bearing with me. This was distributing a power. Distribute the 1/2 to everything inside, break it down. Okay, this was a power to power. We multiply the powers, we keep that base, clean it up, and then evaluate it. All right, down here, a over b to the power of m is equal to a to the m over b to the m. Okay, so what I did was everything inside gets that power of m. So if I give you this example of 16 over 81, and we'll make it to the power of 1/4. 16 over 81 does not divide nicely. But if I break it down and say I have 16 to the 1/4 over 81 to the 1/4, I can put each individually in my calculator, but I want you to come back and think about it. Isn't that the 4th root of 16 and the 4th root of 81? Now, if this wasn't something I could take the 4th root of, I would break it down the best I can, and I'd have to rationalize the denominator. But there is a 4th root of 16, it's 2. And there is a 4th root of 81, it's 3. Okay, so we have a couple more examples here. And you can see that I have numbers here, not variables, but these can happen with variables. And absolutely, I could just type this in my calculator and I could have an answer and have to do no thinking at all. However, you will come across problems with variables. So right now we're really just practicing this. So I am going to simplify each expression. So I want to write it as a single base, okay? So I'm going to keep my base of 25. And then when I multiply bases, I add powers. So I have 3/5 plus 2/5. Okay, I could type 3/5 plus 2/5 in my calculators. We get it, 5 out of 5. But remember, when you add and subtract fractions, you need a common denominator. So I keep the 5, 3 plus 2 is 5. So I really do get 25, 5 over 5, which is 25 to the first. And so my final answer is simply 25. All right, here I have division, and when I have division, I subtract. So I'm going to show that. It's going to be 8 to the 1/3 minus 2/3. All right, so when I go to do that and I simplify, I end up with 8 to the negative 1/3. 1 minus 2 is negative 1. Keep the common denominator of 3. I have a negative exponent, so I'm not even worried about the 1/3. I'm worried about the negative exponent. I'm going to take the reciprocal. Okay, so a to the negative n is equal to 1 over a to the positive n. So we take the reciprocal, and that'd be 1 over 8 to now positive 1/3. And 8 to the 1/3 is the same as the cube root of 8. And so that would give me 1 over 2. You are never to leave a fractional exponent if it can be broken down. It would always go back into root form, and I could take the cube root of 8, so I lucked out. If not, I would be rationalizing the denominator. All right, here are the last 3 problems to try. This is supposed to be indeed a negative sign here. Make it look a little clearer. All right, so I'm going to keep my base of 36, and I'm going to show that I'm adding 3/8 plus 1/8. So that gives me 36 to the 4/8. So to write it as a simplified rational exponent, that'd be 36 to the 1/2. Okay, so that's simplified. And what is 36 to the 1/2? Well, isn't that the same as the square root of 36, which is 6? Final answer. All right, now I have a negative 8 to the negative 1/3. I want to remind you that that negative is a negative number, and that negative is your exponent. It doesn't change the sign of the number. This tells you to flip it. So we would have 1 over negative 8 all to the power of 1/3. Now notice I kept the parentheses, all right, because that negative 8 is a part of the power. And so negative 8 to the 1/3, that's the same as me saying the cube root of 1 over negative 8. Well, the cube root of 1 is 1, and the cube root of negative 8 is negative 2. So you get a negative 1/2. All right, next one we have division. So we're going to keep that base of 5. We're going to take 9/4 minus 1/4, and that gives me 5 to the 8/4. Pretty nice, because 8/4 is the same as 2, and 5 squared is 25. All right, so those are examples. And then I want to show you, it's called a graphic organizer. It just takes some of the main ideas and reminds you some information that we learned from 8.6. So n is called the index of the expression. So there's my index. It's the root we're talking about. All right. The product property applies. So just like we had a square root, we can separate it. Any root can be separated, and here's an example. The new rule, if I have the nth root of a to the m, it's the same as a rational exponent. The root, or the index, is now my denominator. Remember, a root makes something smaller, denominators make something smaller. The power stays on. So here's an example, and then the same thing with division. Just like this, I can break division apart. These two properties, this property and this one up here, they go hand in hand. This is specific to just the nth root of a to the first, and this is the nth root of a to any power. So this is a great organizer to help you remember some of the new rules that we had. Last thing I'm going to say is to make sure you practice this and that you really do know your other properties of exponents that we had gone over also, as well as your negative relationship on exponents.